Alright guys, we're going to the conference room because it's time to continue with our cryptography knowledge mastery. Practical introduction to cryptography. Alright, so last time we looked at randomness and entropy. Today we're gonna talk about random number generators and pseudo random number generators. Okay, random number generator, pseudo random number generator. We're gonna see why they're important. So what are both? A random number generator is a source of entropy and uncertainty, has a source of entropy and uncertainty, right? Truly random. So what can be truly random? We'll see. This one is a cryptographic algorithm, right? This is a source of uncertainty and randomness, right? More. But this, a pseudo-random number generator, is a cryptographic algorithm, so an algorithm has steps, that produces high-quality random bits from a truly random source, right? So this, which is gonna be this one. So a random number generator is a source of entropy that is used in pseudo-random number generators to produce high-quality bits. Now let's look for it a bit more in detail, right? So usually this is based on nature. On the environment. Why am I saying this? Because really you cannot, you have to sample, to get randomness, you have to measure the world. You have to measure, for example, the static noise that the TV makes. That's perfect to sample some random measurement. Or, let me see if they're making another example. A measure of noise, temperature, any kind of thing that you sample from the real world, that's going to be a source of randomness, right? This doesn't come from an algorithm alone. This comes from randomness, from nature and the environment, by sampling nature and the environment. Now, in operating system, another source of randomness, like nature, would be to measure operating system data, which is always randomly changing all the time, mouse movements of humans, which are very unpredictable also, and you know, any human activity or sensors in the computer. These things are also great source of real randomness and random generator. Now, a random number generator truly is non-deterministic. Obviously, because if we sample the, let me make a little dotted line so I can separate the two. That's ugly. Environment, you know, that's environment. Okay. So it's non-deterministic because every time we sample a phenomenon, we don't know what we're gonna get, obviously. It's very analog, so analog source. I can just add it here. Analog source, right? Obviously Max has high entropy. High, I always do an arrow, high entropy. Okay, high entropy, non-deterministic, and is based on nature and analog sources, right? We also have, as open parentheses, quantum random number generators, very expensive, very crazy, and they measure the sample randomness from radioactive decay, for example, or from photons polarization. Very so quantum physical phenomenons, and these are very strong, very good for randomness. But other than that, these can be, again, sensors, hardware, as long as they sample analog sources, nature, environment, and in a non-deterministic way, with a high entropy, they give you random values, right? Now, if that's a random number generator, then what is a pseudo-random number generator? A pseudo-number generator basically solves the problem. So first of all, why was it created? Because it solves the problem of the fact that you don't always have a source of randomness available, and it will be unpractical to always have to source random bits. Also, the non-deterministic nature can be a problem, because what if we want random bits, but we also want a way to retrieve a sequence, right? So that's where pseudo-random number generation came to play. And just looking at my notes 1 second, addition. Perfect. So yeah, they basically algorithm. So this is an algorithm. They basically solve the problem that these are unpractical. So these will always give you random bits all the time. You can always query a pseudo-random number generator at any moment and get your random values back, okay? Well, with this one, we might not have some random measurements at the moment, or we might not have some human mouse movement at the moment. You know, the random events might not be there at that time, so it's unpractical. So what the pseudo-random number generation, it uses a random number generation, I'm going to make a little drawing in a second, is deterministic. Especially if there's a thing called a seed, a common random seed, to which the algorithm grows. We'll see seeds later. And gives you a it's deterministic, and it still gives you good entropy. Okay, so this can already look like side to side. There's no quantum thing here, obviously. So what's happening is that we're having some analog signal, right? Which can be, this is a wave, guys. Oh, I ruined it. I should do in one shot. But I make a wave, an analog wave, right? So this is any measurement of noise, whatever analog measurement, unpredictable from nature is. And we're gonna, the random number generator is gonna take this, sample it, and give us, let's say, a few bits. 1, 0, 0, blah, 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 0, 1, okay? Well, the pseudo-random number generator is gonna sit here, get input, save the input from the random number generator, okay? And this, through a cryptographic algorithm, is gonna give us additional bits. Okay, so you see the original are here, and the pseudo-random creates additional one. Again, because we want to be able to query this algorithm, and anytime, any program in the operating system should be able to call this program and get random bits all the time, even if we don't have any random event sample. But again, random number generation samples numbers, true random numbers, and the pseudo-random number generator works from those to then generate a lot more, okay? So that's it. So let's focus obviously our attention on pseudo-random number generation, because this is a cryptography learning path. And let's see how, let me save some space actually. make the arrows go here. Alright, just save some space on the right. So let's focus on the pseudo-random number generators, right? So how do they work? Basically, every X amount of time, they will take bits from the random number generator. Remember, pseudo-random number generator always starts from a true random number generator. It starts from there. And at every interval of time, which can be, I don't know, X minutes, it will query for more true random values, okay? It will keep querying them, right? And it will store these values in something called an entropy pool. So this is a I'm gonna write it down, entropy pool. Entropy pool. The entropy pool is important because it's a place in memory where the pseudo-random generator will store the random values given by the random number generator, okay? And so every X amount of time, the pseudo-random number generator will get values from the random source and put them in this entropy pool, okay? So we have a pool of random values given by the random number generator. By running the determinism generator. So, how does he do that? He runs everything deterministically, okay? So, input. Perfect. Let me just review my notes 1 second. Here. Okay, perfect. So, let's go on. How does this work? We have 3 steps in a pseudo-random number generator, or at least 3 functions, 3 methods that make this whole thing work. Let's put them here. You have a init method, okay? Init, which initializes the algorithm, and this is called once at the beginning. Obviously, it's the initialization, and it literally initializes the internal state of the program, which in this case it's the mempool. So it clears the mempool, initiates it to a blank state, defaults all the variable, all the memory buffers. It basically gives a fresh state. Okay? Then the other 2 functions are going to be called refresh with some values R. Refresh, you might have guessed right, is what refreshes, right? So it gets some data R. R is some piece of data that we pass to the refresh function, and what this R is values from the random number generator, so these ones. So it will take these R values and populate the mempool, okay? Now this process is also called seeding, okay? This is called reseeding, seeding and reseeding. It's called by the operating system, right? It's called by the operating system every X amount of time, and it grabs new values from the random source, from randomness, from nature, and it puts them in the memory pool. Dates. Not the memory pool, sorry, entropy pool. Right? Appends data. Appends, you see appends. Puts are in entropy pool. Okay, so it puts these new random values in the entropy pool, right? Creating a state. Exactly. So once a refresh is being called, then you can call, we're going to go to the third function, which is next. Okay, let me go back to this one really quick. This is also called seeding. R is the seed, right? And we are seeding our memory pool. This is also another way to call it, because from that seed, then we generate pseudo-random numbers, right? So that's a seeding also. So next we'll return again. N is simply how many bits do we need. So 1, 2, 3, how many whatever bits. So returns N right, returns N random bits. And it does so by going into the memory pool. Sorry, I keep freaking confusing. Memory pool is for miners and blockchain and Bitcoin transactions. It's not for this. This is entropy pool, not memory pool. So it basically, from the entropy pool, will create random bits, right, and return them to the user, to the whoever calls the function. So perfect. So it will return bits and update the entropy pool, because we always want to keep the entropy pool unguessable. Perfect. Why is it important that the entropy pool gets updated after every time we call next? Because we don't want to call next and get the same values from the same memory pool, right? So obviously we're gonna refresh the memory pool. Very good. Now, if this is called by the operating system, can you guess who calls this? The applications, right? Any other application that needs random bits will call a pseudo-random number generator, so we'll call a next kind of function, and to get n random. I need 100 random bits, then I'll call next with 100. All right, so again, we're still on a very high level right now. What are the security concerns of pseudo-random number generation? Let's move on. And how do we address them? So we have mainly two security concerns. Right? One is it's called backtracking resistance. Okay, with backtracking resistance, it basically, which is called forward secrecy, it means that it's impossible to recover previously generating bits. Get previously gen bits, right? Makes sense, because if an attacker I will go over later in the detail, but let me just outline them for now. One is backtracking resistance and the other one is prediction resistance. Okay? And prediction resistance is obviously you cannot guess future bits. Right? If I can guess what the next bits are, it's really not a random number generation and we're gonna have security problems. Now, how do these security concerns are addressed? Well, the backtracking resistance, to make sure that your pseudo-random number generator is backtracking resistant, and so attackers can get, how do you make it in a way that people cannot get previously generated bits? So you do this by making sure that your calls made in refresh and next will be irreversible, okay? Meaning the way you update your entropy pool, the way you see your entropy pool, it should be done, or the way, you know, and you change the state every time, it should be done in an irreversible way, so that an attacker that takes over your machine, your system, your software, whatever it is, cannot determine the previously generated bits, because from the current state of the entropy pool, he won't be able to go back to the previous states of the entropy pool, okay? And so, really important to have these two functions. These two functions are the key for backtracking resistance. Now, what's the key for prediction resistance? This one is a bit more obvious to me. It's that the refresh, this one in particularly for prediction resistance, should be called regularly, right? Should be called regularly, and with true, again, obvious thing, with true random values of R, because if these are, if R are true random values, then again, impossible to predict what's happening next, right? But if I don't use a true source of randomness, then it's much easier to fail on this security point. So again, if an attacker gets a hold, can get access and read in memory, attacks my computer, and can read the entropy pools, he can't tell what's gonna happen next, right? He won't be able to reconstruct, to guess the sequence, okay? So that's very important. Now, let's go through two examples of pseudo-random number generators, right? One of them was Fortuna. You know what the entropy pool is now. Right, we're gonna talk about Fortuna. Fortuna was a pseudo-random number generator used in Windows machines. He's using Windows machines. I didn't catch if it's still used or not, but it's a Windows-based, let's see, construction. Okay, yeah, it's used in Windows, designed in 2003, okay? While Mac OS and iOS use one thing called Yarrow. So Fortuna is for Windows, and Yarrow is for Mac. But we'll talk about Fortuna. Alright, so Fortuna has, again, we're gonna reconnect to the generic steps that we do. So it has 32, Fortuna in particular, this algorithm has 32 memory pools, okay? It has 32 memory pools, and it has a key K and a counter C. So the elements are, wait, let me see, 32. Okay, 32 entropy pools, and then he has, whoa, and then which means from P1, P2, all the way to P32. Okay, and then he has a key k init state, right? When we talk about a state, so when we call init, in this case for this algorithm, we're gonna create 32 empty slots for memory pool in memory. We're gonna create an empty slot for the key, and then we're gonna create an empty slot for a counter. Counter C, okay? Very good. So now that we start with these, how is this process gonna look like? Again, we call init, right? We call init on this algorithm, and so we're gonna create these slots, we're gonna set k to 0, and we're gonna set c to 0, right? We call init. Perfect. Then, perfect, so we called init, we have everything initialized to 0, everything initialized, right? The state is ready. Then, here you go. What's the refresh? What the refresh looks like for this, right? How the refresh code is going to pan out is that the data are from a random source of the operating system, from a random number, is going to be put, well, all initialized. To 0, and then refresh is going to put, we're going to give some R, so it's going to put R into pools. So these P1 to 32 are not going to be empty anymore after refresh, but they're going to store values, right, from a random source, from a random number generator. And then next, when other program are going to call next on Fortuna, what happens is that perfect. What happens is that k is given a value from the entropy pool. Okay, then and then a I mean, which pool from P1 to 32, it depends. I mean, this is like a bit of details of the algorithm, depends on how many times next was called before, from which pool it gets sampled. But the point is that from the entropy pool, you extrapolate a value of k, random obviously, because entropy pool are random numbers. You extrapolate a value from k, and then you encrypt C using k as a key, right? And then you encrypt C with k, okay? So you encrypt the counter, which obviously it grows. Now, if we need more bits than 1, what's gonna happen is that if we need more random bits, then we're gonna keep increasing the counter. Okay, so increase the counter to C+1, and we get a random value. Value 2. Okay, etc, etc, etc. C+2, C+3, depending on how many bits we need, right? How many random values you need. So the point is that we increase the counter, and also that the key, again, updated from the entropy pool, is a random, and it serves to generate the bits. Okay? So, let me see. It looks simple, right? Because we kind of broke it down in very simple steps, but it's very hard to implement this correctly because there's a lot of tiny details. So for example, how do you behave when you're not receiving random? I mean, if we're getting into the code of how to implement this, it's obviously nasty because we have to guarantee perfect, because it's something that deals with security, right? Generation of random values. So obviously the implementation of this is not straightforward, it's hard. There's a lot of tiny details that need to be considered. So What's the biggest risk in Fortuna though? It's, yes, the implementation details, but something important is the seed file, right? Fortuna is based, shouldn't use this as the same title, but Fortuna uses this thing called a seed file, because the seed file is used in the refresh, right? In the refresh operation. And let me just make sure something. Fortuna, yeah, exactly. And so, let me see, the refresh call. Yeah, exposing the seed files, right? Exactly. So since Fortuna doesn't get all of its value in the refresh function from, it doesn't always get always random. It also uses a seed file, so pre-loaded values to populate the entropy pool. So this means that if you steal my seed file, you're going to be able to generate the same number of random bits, right? So if I have a roulette software that will spin randomly every time, you're gonna be able literally to guess what number in the roulette will come out, because you know my seed file, you know my randomness number, and from there you can figure out the rest of my program, how my program behaves, okay? So very important in Fortuna, the seed file, and in general pseudo-random number generators, the seed, right? Now what's important in the seed is that it's also a good thing, because if you want to have the same numbers, we use the same seed. It's just a deterministic, it's to make everything deterministic, okay? So very important. Now, there's two types of pseudo-random number generators, the cryptographic and non-cryptographic ones. The cryptographic ones are unpredictable, right? They have strong operational mechanisms inside. So okay, so crypto versus non-crypto pseudo-random number generators. And so, again, one pseudo-random number generator is cryptographical. Again, if all the mechanism make sure that everything that spits out is not guessable and is unpredictable. But a non-crypto pseudo-random number generator, a non-cryptographical one, is not secured from predictability attacks and is only concerned about giving a uniform distribution. So, pseudo-random number generators, right? Their goal is to give you random bits in a way that they all look, if you call this 100,000 times, they all look random, right? So it distributes uniformly statistics. It gives out bits in a statistical uniform way, right? That's what kind of random is. But the problem is that not all the pseudo-random number generators are resistant to predictability attacks, okay? And a little note to programmers. I was surprised when I read this, but the random module in Python, the random class in Ruby, the libc in the C language, the random drand48, and the rand and empty rand of PHP, so C, Ruby, PHP, and C, they all use non-cryptographic pseudo-random generators, right? In their, for example, in their rand function in C or rand function in PHP, it's non-cryptographical. So what happens is that when programmers use those functions in cryptographical applications, it's a disaster, because using a non-cryptographical pseudo-random number generator to, for example, create keys for wallets, for whatever you are, disaster because attackers are able to break non-crypto PRNG. So let's look at an example of a non-cryptographical pseudo-random generator. Wait, let me mute the notifications. Okay. So, I lost 1 second. So, give an example of a non-cryptographical pseudo-random generator. Let's look at the Mersenne twister. Let's see. Right, the Mersenne twister basically, I'm not gonna go too much in the detail of it, but again, it follows the same general principles of a pseudo-random number generator. So we have a state which gets updated, and then we pull things down. So it starts like this. Let me see, I need the notes closed because it's a bit hard. So Mersenne twister is a non-cryptographical pseudo-random number generator. It starts with an array of S1 until S624, okay, and then it evolves into an S2 until S625. This is a 4. And then again, S3, 66, 600, etc., etc. So the states updates as y. According to what equation? And it's important. I mean, I'm going to write the whole equation. You don't need to know the equation, but it's important. The change of state is done according to S of k plus 624 is equal to, yes, state of k plus 397. Oh boy, I don't have space here. Such a nasty formula. Well, nasty. I know there's worse, but 624 397. And again, don't worry about the details here. What important is this XOR. Then A is a function that encrypts S of k and a number. Or S of k plus 1 and then another hex number, F, a bunch of times. Perfect. So what's happening again is that we have I'm gonna give you a more visual representation of this. Is that we have a seed, right? We call the init function, and we get state 0, where we get the first state, and then we do this thing called a twist, and we get state 1 according to, right, this whole formula, and then we do according to state 2 if you refresh, right? The twist is basically a refresh call. Again, we can only go one way from state to state because of the backtracking resistance. An attacker cannot go back and guess the other states. And then we use these from each state we get down the actual random numbers as random 1 and random 2. Now let me make this a little bit more visual even, because what the state looks like in a Mersenne twister is that, imagine this is an array and these are 3, this is 1, right? And this is 624. 624. So that means that I can generate, and then what happens, then I twist again, and I get another array with different values. okay? And from each value we call the next, when we call the next function, we'll get random 1, random 2, random 3, blah, 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 until random 624. Okay, so we get a bunch of random values from each state, okay? So this is the Mersenne twister. The author did not really do a good job explaining it. It's a bit cryptic in the way he puts it in the book. But the point that I got is that why is this non-cryptographical and why is this insecure? Is because we use a linear combination. XOR, it's a linear combination, so it's very easy and predictable to do XOR operations back and forth, right? In fact, does this give an estimate? Yeah, exactly. Linear combinations are predictable, okay? Now, how would we make the Mersenne twister cryptographically secure? Instead of using a XOR operation, we would use, for example, products and combinations, because if we use products and AND combinations, instead of having a predictable equation, we have a non-predictable equation, because we have much more let's see, linear combinations of those bits include at most 624 variables, right? Non-linear combination allow for up to, okay, there we go, this is the key, 2 to the 624 variables, okay? So this is linear. This is linear. So we have 624, you know, I'm not grasping exactly how the math works, but we have only 624 possible outcomes. Yeah, exactly, 624. But again, if we use the non-linear equations, we would have had a 2 non-linear, we would have an equation of 2 to the 624. Okay, so an equation with 624 variables, doable, especially by computers, but an equation with 2 to the 624, this is such a huge number, you guys have no even idea. 2 to the 300 is already like some crazy number about the information in the atoms in the universe or something. So 2 to the 624 is a huge number, and that's how you would make the Mersenne twister cryptographically secure, because with XOR, the way it is now, it's not cryptographically secure. Now, is that a bad thing? Not necessarily, because if we need random numbers for our video game, for our scientific experiment, a non-crypto random number generator is very convenient. Because why? By using simple linear equations to generate random numbers, it is fast. It is fast. But if we had to use non-linear and so unpredictable outcomes, that would be a much more work to do for the processor, for the CPU. So that's why it's important to kind of cover this. And then the author makes a little bit paragraph about the uselessness of statistical tests. I'm gonna separate this from the rest because it's a bit of a statistical test. Now, they're useful if you wanna see how much your algorithm spits out good uniform results, outcomes, but it is not, the author makes a point that is not a way to determine cryptographic security, okay? It's not a way to identify the cryptographical security. So, okay, not okay to test for they're not okay to test them for cryptographic security, because any even a weak, like we say, even the Mersenne twister can satisfy a statistical test and produce a lot of randomly distributed numbers, but it will not satisfy, it will not be cryptographic security. So do not use statistical tests to test for cryptographic security of your pseudo-random generator. And wow, 45 minutes of video, and this concludes this topic of, not concludes the topic, but this concludes this introduction, this overview of random number generators and pseudo-random number generators, okay? I'll have to look a little bit more into how exactly the Mersenne twister works, but again, I put this formula just to make you understand that it uses a linear equation, right? And so this is why it's non-cryptographically secure, and this is why you shouldn't be using the Mersenne twister, the classic one, for cryptographic applications. All right, so I think we're done for today. I really thank you if you were watching, if you watched all the way here. I mean, you are motivated and you really want to learn cryptography. Thank you so much for staying with me, for watching video. Hope you understand. If you have questions, anything, leave a comment, please. Let's all have discussions together about pseudo-random and random number generators. It's a very interesting topic. This is what you would hack if you want to guess the casinos, online casinos, next number in the roulettes. They're all generated. This is what's behind all of this. I don't know now the modern ones if they use some kind of probably fair mechanism. How does that work exactly? But you know, it is that's what it is. All right, thank you so much. I'm not gonna take you here hold you here any longer. I'll see you next time with real world pseudo-random number generators. We might even look at some code. All right guys, see you next time. Bye bye. Thank you for watching. Leave a comment, like and comment and subscribe. Bye, ciao.